As you settle into this moment of relaxation, perhaps already feeling the gentle pull of drowsiness, you're about to embark on an extraordinary journey through one of the most fascinating and mysterious processes your body performs every single day. Sleep isn't simply the absence of wakefulness. It's an intricate symphony of biological mechanisms that orchestrates some of the most important restoration and maintenance work your brain and body will ever experience. Right now, as you listen to these words, your brain is actively producing a molecule called adenosine. Think of adenosine as your body's natural sleep currency, accumulating with every moment you remain awake, every thought you think, every movement you make. This remarkable molecule builds up in your neural circuits throughout the day, particularly in areas of your brain responsible for maintaining alertness and attention. The longer you stay awake, the more adenosine accumulates, creating what scientists call sleep pressure, an increasingly powerful biological drive that will eventually compel you toward rest. What makes this process truly fascinating is how adenosine works as a master regulator. As levels rise, adenosine begins binding to specific receptors in your brain, particularly in regions like the basal forebrain and hypothalamus. This binding acts like a dimmer switch on your consciousness, gradually reducing the activity of wake-promoting neurons, while simultaneously activating sleep-promoting pathways. It's as if your brain has an internal accountant, meticulously tracking your wakefulness debt and preparing the perfect conditions for biological repayment. But adenosine doesn't work alone in this magnificent choreography. Your circadian rhythm, that ancient internal clock that has guided life on Earth for millions of years, provides the temporal framework for your sleep-wake cycle. Deep within your brain, in a small cluster of neurons called the suprachiasmatic nucleus, approximately 20,000 cells work in perfect synchronization, creating oscillating patterns of activity that repeat every 24 hours with remarkable precision. This circadian clockwork responds exquisitely to light, particularly the blue wavelengths present in morning sunlight. When photons enter your eyes and strike specialized cells in your retina, they send signals directly to your circadian control center, essentially telling your brain what time it is in the natural world. As daylight fades and darkness approaches, your pineal gland begins producing melatonin, often called the hormone of darkness. Melatonin doesn't directly cause sleep, but rather signals to your body that nighttime has arrived and it's time to prepare for rest. The interaction between your homeostatic sleep drive, governed by adenosine, and your circadian rhythm creates what sleep scientists call the two-process model of sleep regulation. During the day, as adenosine accumulates and sleep pressure builds, your circadian system helps you stay alert, fighting against the mounting pressure to sleep. But as evening approaches and melatonin levels rise, these two systems align, creating the perfect biological conditions for the transition into sleep. This transition isn't an instant switch from consciousness to unconsciousness. Instead, it's a gradual progression through distinct stages, each characterized by unique patterns of brain activity that serve specific biological functions. Your brain doesn't simply shut down during sleep. Rather, it shifts into different modes of operation, each optimized for particular types of restoration, memory processing, and physiological maintenance. The architecture of sleep reveals itself through the electrical signatures of your brain waves, which can be measured and analyzed to understand exactly what's happening in your neural circuits throughout the night. As you begin to drift from wakefulness into the first stage of non-REM sleep, your brain waves slow down from the rapid beta waves of alert consciousness to the gentler alpha waves of relaxation, eventually giving way to the even slower theta waves that characterize the lightest stage of sleep. Stage 1 of non-REM sleep represents the twilight zone between waking and sleeping, a liminal space where consciousness gradually fades but hasn't yet fully relinquished its hold. Your muscle tone begins to relax, your breathing becomes more rhythmic, and your brain starts to filter out external sensory information. This stage typically lasts only a few minutes, serving as a bridge between the bustling activity of wakefulness and the deeper restoration that awaits. As you progress into stage 2 of non-REM sleep, your brain begins producing distinctive electrical signatures called sleep spindles and K-complexes. Sleep spindles are brief bursts of rhythmic brainwave activity appearing on brain recordings as spindle-shaped patterns that give them their name. These fascinating electrical events generated by your thalamus help protect your sleep from external disturbances by preventing sensory information from reaching your conscious awareness. It's as if your brain constructs an electrical barrier, allowing you to remain asleep despite sounds and other stimuli in your environment. The real magic, however, begins as you transition into stage 3, also known as slow-wave sleep or deep sleep. This is where the most profound restoration occurs, where your brain orchestrates some of its most important maintenance functions. During slow-wave sleep, your brain produces large, synchronized delta waves, reflecting a state of profound neural coordination that creates optimal conditions for cellular repair, memory consolidation, and waste clearance. Perhaps one of the most remarkable discoveries in recent sleep science has been the identification of the glymphatic system, a sophisticated waste clearance network that becomes highly active during deep sleep. Think of this system as your brain's nighttime sanitation crew, working to remove the metabolic waste products that accumulate during waking hours. The glymphatic system represents one of the most extraordinary discoveries in modern neuroscience, fundamentally changing our understanding of why sleep is not just beneficial, but absolutely essential for brain health. During slow-wave sleep, the spaces between your brain cells actually expand by up to 60%, creating highways for cerebrospinal fluid to flow through your neural tissue like a cleansing river. This fluid carries away toxic proteins, including amyloid beta and tau, the same proteins that accumulate in neurodegenerative diseases like Alzheimer's. The discovery of this system has profound implications for our understanding of brain aging and disease prevention. Research now shows that people who consistently get inadequate deep sleep have higher levels of these toxic proteins in their brains, suggesting that poor sleep may accelerate cognitive decline and increase the risk of dementia. The glymphatic system essentially serves as your brain's nightly reset button, clearing away the molecular debris of consciousness and preparing your neural circuits for another day of optimal function. The relationship between sleep and memory formation reveals another layer of complexity in the sleeping brain. During slow-wave sleep, your brain doesn't simply rest. It actively replays and consolidates the experiences and information you encountered during the day. The hippocampus, your brain's primary memory formation center, engages in a sophisticated dialogue with the cortex, transferring important memories from temporary storage to long-term repositories. This process involves the generation of sharp-wave ripples, brief but intense bursts of electrical activity in the hippocampus that coordinate with cortical sleep spindles to strengthen neural connections and integrate new information with existing knowledge. It's during this phase that your brain decides what information is worth keeping and what can be forgotten, essentially curating your memory collection while you sleep. The coordinated dance between different brain regions during memory consolidation represents one of the most elegant processes in neuroscience. Sleep spindles, those protective electrical signatures we encountered earlier, work in concert with slow oscillations to create windows of opportunity for memory transfer. When these brain rhythms align perfectly, memories flow from the hippocampus to the cortex, like data being transferred to permanent storage, ensuring that important information survives and integrates into your long-term knowledge base. As the night progresses, your sleep architecture follows a predictable pattern, cycling through different stages in approximately 90-minute intervals. Each cycle brings you through the progression from light sleep to deep sleep, before transitioning into one of the most fascinating and mysterious states of consciousness known to science, REM sleep, or rapid eye movement sleep. REM sleep shatters many of our intuitive assumptions about rest and restoration. Far from being a quiet, restful state, REM sleep represents a period of intense brain activity that rivals and sometimes exceeds the neural firing patterns of wakefulness. During REM sleep, your brain becomes a theater of vivid experiences, generating the rich narrative dreams that have captivated human imagination for millennia. Recent research has challenged many long-held beliefs about REM sleep and dreaming. While scientists once believed that dreams occurred exclusively during REM sleep, we now know that dreaming can happen during any stage of sleep, though REM dreams tend to be more vivid, emotional, and narratively complex. The unique electrical signature of REM sleep involves theta waves, rhythmic oscillations at 5 to 8 Hz that remain curiously confined within the skull, unlike other brain waves that can be easily detected by external electrodes. This confinement of theta waves creates what researchers call the REM paradox. While external brain monitoring shows what appears to be wake-like activity, the true electrical signature of REM sleep, those powerful theta oscillations, remains hidden from standard polysomnography. This discovery has revolutionized our understanding of what REM sleep actually represents at the neurophysiological level. During REM sleep, your brain orchestrates a remarkable physiological transformation. Most of your voluntary muscles become temporarily paralyzed through a sophisticated mechanism involving the brainstem release of neurotransmitters like glycine and GABA. This sleep-induced paralysis, mediated by the pontomedullary reticular formation, prevents you from physically acting out your dreams, protecting you from potential injury during episodes of vivid dream activity. The paralysis of REM sleep represents an elegant evolutionary solution to the problem of dream enactment. Imagine if your motor neurons remained fully active while you dreamed of running, fighting, or flying. The temporary disconnection between your dreaming mind and your voluntary muscles allows for the full expression of dream consciousness while maintaining physical safety. This paralysis mechanism occasionally malfunctions, leading to a condition called REM sleep behavior disorder, where individuals physically act out their dreams. Studying this condition has provided valuable insights into the normal protective mechanisms of REM sleep and has also revealed important connections between sleep disorders and neurodegenerative diseases. The content and meaning of dreams have fascinated humans throughout history, and modern neuroscience is beginning to unravel some of the mysteries surrounding these nocturnal mental productions. Dreams appear to serve multiple functions, from emotional processing and trauma integration to creative problem-solving and memory consolidation. The emotional intensity of many dreams reflects the heightened activity of the limbic system, particularly the amygdala during REM sleep. The prefrontal cortex, responsible for logical thinking and reality testing, shows decreased activity during dreaming, which may explain why dream logic often seems perfectly reasonable within the dream state, despite being bizarre by waking standards. This selective deactivation of critical thinking regions allows for the fluid, associative thinking that characterizes dream consciousness and may contribute to creative insights and novel problem-solving approaches. Lucid dreaming, the phenomenon of becoming aware that you're dreaming while still in the dream state, represents a unique form of consciousness that bridges waking awareness and dream experience. Research into lucid dreaming has revealed fascinating insights into the nature of consciousness itself and has practical applications for treating nightmares and phobias. Sleep paralysis, though often frightening, represents a normal aspect of REM sleep physiology that occasionally intrudes into waking consciousness. When people become aware while still in the paralyzed state of REM sleep, they may experience the terrifying sensation of being unable to move, while often hallucinating disturbing presences or sensations. Understanding the neurobiological basis of sleep paralysis can help reduce the fear and anxiety associated with these experiences. Nightmares, those disturbing dreams that can wake us in distress, serve important psychological functions related to emotional processing and threat simulation. Current research suggests that nightmares may help us practice responses to dangerous situations in a safe environment. Though excessive nightmare frequency can become problematic and may indicate underlying stress or psychological issues, the relationship between sleep and physical health extends far beyond brain function. During sleep, your body releases growth hormone, crucial for tissue repair and development. Your immune system becomes more active, producing infection-fighting cells and antibodies that help protect against disease. Sleep also plays vital roles in regulating metabolism, appetite hormones, and blood sugar control. The consequences of sleep deprivation demonstrate just how essential sleep is for optimal functioning. Chronic sleep loss has been linked to obesity, diabetes, cardiovascular disease, and compromised immune function. Even a single night of poor sleep can impair cognitive performance, emotional regulation, and decision-making abilities, highlighting the immediate importance of adequate rest. Temperature regulation represents another crucial aspect of sleep physiology. Your core body temperature naturally drops as bedtime approaches, signaling to your brain that it's time to sleep. This temperature decline is partly orchestrated by melatonin and helps facilitate the transition into sleep. Maintaining a cool sleeping environment, typically between 60 and 67 degrees Fahrenheit, supports this natural temperature regulation and promotes better sleep quality. Light exposure plays a crucial role in maintaining healthy sleep patterns. The timing and intensity of light exposure throughout the day helps synchronize your circadian rhythm with the external environment. Morning light exposure, particularly from natural sunlight, helps establish a strong circadian signal and promotes alertness during the day while supporting better sleep at night. Conversely, excessive light exposure in the evening, particularly blue light from electronic devices, can suppress melatonin production and delay sleep onset. Understanding these light-based mechanisms allows for the development of effective sleep hygiene strategies that work with your natural biological rhythms rather than against them. Sleep hygiene encompasses a range of behavioral and environmental factors that promote consistent quality sleep. Regular sleep schedules help stabilize your circadian rhythm, making it easier to fall asleep and wake up at consistent times. Creating an optimal sleep environment involves managing factors like light, noise, temperature, and comfort to create conditions that support natural sleep processes. The role of caffeine in sleep regulation demonstrates the delicate balance of neurochemical systems that govern wakefulness and sleep. Caffeine works by blocking adenosine receptors, temporarily preventing the buildup of sleep pressure. However, caffeine's effects can last 6 to 8 hours, meaning that afternoon coffee consumption can interfere with nighttime sleep even when you don't feel actively stimulated. Alcohol presents another complex interaction with sleep systems. While alcohol may initially promote drowsiness and help with sleep onset, it disrupts sleep architecture throughout the night, particularly reducing REM sleep and causing frequent awakenings. Understanding these interactions helps explain why alcohol, despite its sedating effects, doesn't promote truly restorative sleep. Exercise influences sleep through multiple pathways, including temperature regulation, stress reduction, and adenosine accumulation. Regular physical activity generally improves sleep quality and can help with both falling asleep and maintaining sleep throughout the night. However, vigorous exercise close to bedtime can be stimulating and may interfere with sleep onset. Individual differences in sleep needs and patterns reflect the remarkable diversity of human biology. While most adults require 7 to 9 hours of sleep per night, some individuals naturally function well on less sleep, while others need more. These differences appear to have genetic components and may be influenced by age, lifestyle, and health status. The aging process brings predictable changes to sleep architecture and timing. Older adults typically experience decreased deep sleep, more frequent awakenings, and earlier bedtimes and wake times. Understanding these natural changes can help distinguish normal age-related sleep changes from sleep disorders that may require treatment. Sleep disorders affect millions of people worldwide and can significantly impact quality of life and health outcomes. Sleep apnea, characterized by repeated breathing interruptions during sleep, not only fragments sleep but also poses serious health risks, including cardiovascular disease and cognitive impairment. Recognition and treatment of sleep disorders represent crucial aspects of preventive health care. Insomnia, the most common sleep disorder, involves difficulty falling asleep, staying asleep, or waking too early. Chronic insomnia can create a vicious cycle where worry about sleep further interferes with the ability to sleep naturally. Cognitive behavioral therapy for insomnia has emerged as an effective non-pharmaceutical approach to breaking this cycle and restoring healthy sleep patterns. The modern world presents unique challenges to natural sleep patterns. Shift work, jet lag, and the ubiquity of artificial light create mismatches between our internal biological rhythms and external demands. Understanding these challenges allows for the development of strategies to minimize their impact and maintain healthy sleep despite environmental disruptions. Technology offers both challenges and opportunities for sleep health. While screens and artificial light can disrupt sleep, technological innovations like smart lighting systems, sleep tracking devices, and specialized apps can also support better sleep habits when used appropriately. The social and cultural aspects of sleep reflect its fundamental importance across human societies. Every culture has developed practices and beliefs around sleep, recognizing its essential role in health and well-being. Modern research validates many traditional sleep practices while also revealing new insights that can inform contemporary approaches to sleep health. As we continue to unravel the mysteries of sleep and dreaming, new frontiers in sleep science emerge regularly. Research into sleep's role in creativity, emotional processing, and spiritual experiences expands our understanding of consciousness itself. The intersection of sleep research with artificial intelligence, genetics, and personalized medicine promises to revolutionize how we understand and optimize sleep for individual needs. The practical implications of sleep science extend into every aspect of daily life. Educational systems are beginning to recognize the importance of sleep for learning and academic performance. Healthcare providers increasingly view sleep as a vital sign alongside traditional measures like blood pressure and heart rate. Workplace policies that consider sleep needs can improve productivity, safety, and employee well-being. As you prepare for your own journey into sleep tonight, remember that you're not simply shutting down for the night. You're entering a sophisticated biological process that will restore your brain, consolidate your memories, clear away metabolic waste, and prepare you for tomorrow's challenges and opportunities. Sleep represents one of evolution's most elegant solutions to the complex demands of maintaining a sophisticated nervous system in a dynamic world. The science of sleep continues to evolve, revealing new layers of complexity and beauty in this most fundamental of biological processes. Each night offers an opportunity to support your brain's natural restoration mechanisms, to allow the glymphatic system to perform its essential cleansing functions, and to emerge refreshed and renewed for another day of conscious experience. Rest well, knowing that as you sleep, your brain is performing some of its most important work, orchestrating the intricate symphony of restoration that makes tomorrow's awakening possible. Sweet dreams, and may your journey through the stages of sleep be both restorative and illuminating.